Good day. There are many different kinds of fluids that exist in the natural world, but for the most part we're having to deal with really just two, air and water. And we've spoken about viscosity in another video, but today I'd like to speak about another property of fluids, namely the density of fluids. Now, when you look at the properties of a fluid like water, one of the important aspects of those properties is that water is an incompressible fluid. When you put pressure on water, all it does is increase its pressure, and you change the volume very little. Now, you'll recall that density is the ratio of mass over volume, and so when you have an incompressible fluid, when you put pressure on it, you are not changing its density at all. That's not quite the case with air. Air is a compressible fluid, but if you look at the kinds of pressures that are important for most biological systems, you can find that air essentially behaves as an incompressible fluid. Just a couple of quick figures to convince you of this. If you look at the typical kinds of pressure differences that exist in biological systems with air, you're talking about pressure differences on the order of 10 to 20, maybe in extremes up to 100 pascals or so. If you compare the change of volume that results from that kind of a change, from that kind of a pressure, 10 pascals or so, then the volume of that air will change only about 0.03%. And so you can treat air essentially as an incompressible fluid. Now, this doesn't mean that you cannot change the density of either liquid, water, or air. In fact, you can change the density quite a bit. One of the ways you can do it is by changing temperature. And just to compare with the figure for pressure-induced changes of volume, when you compare the effect of a 10 degrees Celsius increase of temperature, what that has on the volume, the air will expand. You're talking about an increase of volume on the order of 3 to 5% or so. So you're talking about a difference of volume that differs by about 3 or 4 orders of magnitude between pressure-induced changes of volume and temperature-induced changes of volume. Now, it'll come as no surprise that when you talk about temperature differences, that can translate into differences of air density and water density, and this can lead to a variety of very important density-related phenomena that go under the general term of natural convection. Now, what I'd like to do right now is to demonstrate to you a quite nice example of how temperature can change density, and to do so we're going to use a classic and quite beautiful instrument called a Galileo's thermometer. And if we look over here at the Galileo's thermometer, I'm just going to bring it into my field of view right here. This is the instrument itself, and you can see it's quite pretty. It consists of a number of glass globes that are filled with liquid, and there are nice brass tags that are hanging from that. Those are containers of liquid that impose a constant volume on the object, and as you can see, some of them float in the water and some of them have sunk in the water. Now, these are filled with liquids of differing densities. You can quite easily do that by putting in different amounts of alcohol into these little bubbles and then sealing them off. But the main thing to point out is that the liquid in there will expand with temperature, but the liquid contained in the volume will stay constant because it's contained within the volume of the bubble. It doesn't apply to the water outside, however, because this can expand or contract as it's heated up. And the way the Galileo's thermometer works is that as this liquid gets warmer and warmer, eventually its density, it's going to expand and its density will decrease. And when it decreases below a certain critical value, one of these will sink, and they'll sink one after the other. Now, we're going to demonstrate this with my handy heat gun right here. We're going to take this heat gun and we're going to apply it to the Galileo's thermometer, and you can see that the temperature here is at a temperature where one of these has sunk and the others are floating, and we'll just apply our heat to this and watch what happens. Very, very quickly, we're applying heat to the water. Its density is increasing. Sorry, I beg your pardon. Its density is decreasing. And after a few seconds, you will see one of these begin to abruptly sink. The Galileo thermometer is sensitive enough so that the heat of your hand will actually change the temperature sufficiently to cause some of these to sink and some not. But it does have a certain volume to it, so it will take a little while for the temperature of that mass of water to it will take a little while for the temperature of that mass of water to decrease sufficiently for these to fall. Now you can see that two of them are falling. So the density has increased and they're coming to rest now. Right now they are at equal density to the water, and as it gets warmer and warmer and warmer, you'll see the one in green start to sink further. And as it gets warmer still, the one in red will eventually start to sink. And there it goes right there. And as the residual heat that we've applied continues to heat the water, you can see that these other balls are continuing to sink. Okay, so the fact is you can actually change the density of water sufficiently to be able to do work on this system. And of course, the work on this system is represented by the tendency of these little glass bubbles to move up or down. Now, they move up or down because there's a force being exerted on them. And the force that's being exerted on them, of course, is gravity, pulling them down. But they're also being held up by a force, that's density, and that's buoyancy. And as the density of the water decreases, the buoyant forces decline and allows gravity to actually take over and move these bubbles up and down in the column of water. Okay, now, the differences of density that exist amongst different fluid masses is sufficient to move these bubbles up and down in the Galileo thermometer, but it also helps explain how different masses of fluids and liquids can interact. And one of the big problems that living things have to deal with in fluid systems is how you get different fluid masses to mix. In our own lungs, for example, we have to deal with two fluid masses that have to be mixed somehow in our lungs to provide the physiological function that lungs do. You have an air mass outside, fresh air, and then you have an air mass inside in the lungs. And one of the challenges of getting these things to behave properly is to get these two masses to mix properly. This mixing problem is actually quite common in lots of situations. It is involved in regulating a temperature close to the ground, for example. It's involved in various kinds of weather systems and those sorts of things. And so one of the things that fluids of different densities do is that they tend to resist mixing to a degree. And we're going to demonstrate mixing between two different fluid masses using a non-toxic dye, fluorescein dye. We're going to be taking fluorescein dye in this syringe right here. It's completely non-toxic. It's actually used quite commonly to trace out leaks in drinking water supplies. And we have a small tube here that's going to enable us to very precisely introduce a drop of fluorescein into a graduated cylinder right over here. And what we're going to do is we're going to look at how that drop interacts with the water in there. Now, fluorescein dye is a little bit more dense than water, and what you'll see is the drop will tend to sink, but as it sinks, you'll see mixing. Okay, now we need to do this very, very carefully. What we're going to do is we're going to get a little drop of fluorescein out there. We want it so that it's right at the edge. We're going to stick the tube in there like so, and we're going to squeeze out a little drop like so. Now you can see the drop is sinking, and fluorescein is a very, very powerful dye, and you can see that it's mixing on the way down, but there's still quite a bit of integrity of the two fluid masses. The fluorescein has followed streams that are quite separate and quite distinguishable from the water. Up here at the top you can see there's still quite a bit of integrity there. It's a very, very self-contained stream. But as this drop sinks, it tends to mix more and more, and you can see the fluorescein dye tends to spread out as the drop makes its way down to the bottom. You might also see that as it makes its way to the bottom, the sinking rate declines. And the reason the sinking rate declines is that as the water and the fluorescein mix with one another, the different densities that initially led to the sinking tend to even out, and it ends up sinking more slowly. Okay, and so when you get different kinds of masses interacting with one another, then you have an inherent tendency to resist mixing, particularly if those fluid masses differ somewhat in their density. Now, when you talk about how density can be changed by things like temperature, this can illustrate a mechanism, or this can power a very important mechanism for mixing of different fluid masses. And to demonstrate that, again, we're going to turn to fluorescein dye, but we're going to use a little bit of a different apparatus now. We're going to take a tub of water, a flask of water, and we're going to introduce a drop of fluorescein in the bottom, and when it's introduced at the bottom, of course, it won't sink. It'll tend to hold together quite nicely, we hope. And then we're going to illustrate how a variation of density can actually help promote mixing. We're going to do that by introducing a little bit of heat right down below the blob of fluorescein. And what that's going to do is it's going to provide a localized increase of temperature, and therefore a localized decrease of density at the fluorescein drop. And we'll see quite an interesting pattern of mixing. All right, so we will take our fluorescein dye. We'll take our fluorescein dye here, and we'll introduce our little pipe, and we'll very, very gently squeeze out a drop of fluorescein dye. And if we're very, very careful about it, as I'm trying to do right here, we will see that the fluorescein dye tends to maintain its integrity quite nicely. And we had a little bit of a squirt there. You can see a little bit of a plume being generated there, but for the most part, the fluorescein blob has held together quite nicely. We're going to take our heat gun again, and we're going to apply heat underneath, like so. Now, if we watch this closely, we will see a couple of things happening. We can see that along the edges that the fluorescein blob is maintaining its integrity quite nicely. But as it starts to heat up, you can see a little plume starting to rise right there. You can see that coming up around the outside. Now, in that instance, what we're doing there is we are providing a localized decrease of density at the fluorescein dye. And if the reduction of density is sufficient, it imparts a buoyant force to that fluorescein dye and allows mixing. And this kind of density-induced mixing is quite common, particularly at areas close to surfaces like leaves or the ground or skins or those kinds of things. Any kind of an interface between an organism, a living system, and its fluid environment. Okay, so that's we see now that the fluorescein dye is mixing very, very nicely, and that point is illustrated well. And that's all for today, and we will see you another time.